In multivariable calculus, you learned something called the dot product. You remember?
Yes.
If you have, say, A1, A2, A3, dotted with another vector, B1, B2, B3, what's the dot product?
A2,
A1,
A1, B1,
B1 plus
A2,
A2, B2
plus
plus
A3.
A3, B3, right? Okay. And we know that if I call this vector u and call this vector v, then u dot v, which is this quantity, will be equal to the norm of u times norm of v times norm the cosine of the angle between. So this is the angle between u and v. And the way we show that is something like this. First, we talk about the norm of a vector. How do you calculate the norm of a vector? It's just the Pythagorean theorem, right? You take the square root of the square sum of all the coordinates, which just follows from Pythagorean theorem. And then we can draw a triangle. So if you have u vector here and v vector here, then if you do v minus u, you get this vector, v minus u. And I know that because u plus v minus u would make u cancel and you get v, which is exactly that one. And this plus this is by the triangular law of addition of vectors that this plus this is the same as that. Right? So we know that. And then if I say this angle is theta, we have, well, if this angle is, no, if this angle is 90 degrees, if it's like u and v and then this is the other one, v minus u, then if it's 90 degrees, we know that the Pythagorean theorem is true, right? The square, or we can say that v minus u squared, norm squared, length of this squared is the norm of v squared plus norm of u squared. But what do you do if this angle is not 90 degrees? If it's in general like that? Well, compared to 90 degrees, if the angle goes smaller, right, then this length becomes smaller, right? So you have to subtract something. And what do you subtract? That's called the cosine law. Cosine law is that you have to do norm of u times norm of v times the cosine of the angle between. Now, if this looks foreign, just think of this. If you have angle C as this as C and this length is, no, usually you put the angle as capital, side length as lower.
Isn't that the law of cosine?
Yeah, that's the law of cosines, right? C squared is equal to a squared plus b squared minus 2ab cosine C. I'm just rewriting this with different letters, and I'm just trying to point out that it's really the Pythagorean theorem modified by the cosine so that it still would kind of make it true for arbitrary angles. Okay. Have you looked at the cosine law that way? If you haven't, you should really think of it that way. Yeah. So that eventually when theta closes down at 0, then you end up with something like this plus this. So this length is just simply this minus that, which is a squared plus b squared minus this. When cosine theta is 0, cosine 0 is 1, right? So you get this, so that's like a minus b squared. So that if you solve for it, you get a minus b, which is this length.
So in mathematics, we don't call that?
If I look at what this is, what is this? This is V, that's U. So V minus U would be B1 minus A1. So V minus U would be B1 minus A1, B2 minus A2, B3 minus A3. So if you take this length squared, it'll be B1 minus A1 squared plus B2 minus A2 squared plus B3 minus A3 squared. That's what you get for V minus U norm squared, right? On this side, this is V squared. V squared will be B1 squared plus B2 squared plus B3 squared, this one. And U squared would be A1 squared plus A2 squared plus A3 squared minus 2 times U V cosine theta. And then if you view this as an equation for this as the unknown, here's what happens. If you expand all this, this is B1 squared minus 2A1B1 plus A1 squared, right? And this one is B2 squared minus 2B1A2, B2A2, or A2B2, plus A2 squared. And the third thing is B3 squared minus 2A3B3 plus A3 squared. And this thing is still equal to that, and then you see a lot of things common in the left and right. What are the common things on the left side and the right side? What do you see in both left side and right side? B1 squared, right? So that cancels. And then
B2 squared.
B2 squared, B3 squared, those cancel away. What else? A1 squared, A2 squared, A3 squared, those cancel away. And then you divide by -2, all the negatives go out. And now you have this identity that this is indeed equal to this. So I just proved this, right? And we call this thing, this quantity, as U dot V. Okay. Now, for some reason, because it saves people having too many parentheses in many scenarios, people rewrite this as U comma V with angled brackets. And it's the same thing, but people call this one as an inner product. Okay. So, assuming that we know what this means, properties of the inner product. All right. So first, and I'm not going to write it as U dot V. I'm now going to use the angled brackets because it saves us having a lot of parentheses when we do it, when you use it for linear algebra. Okay. So one thing that we know is that it's a symmetric thing. Right? Whether you do U dot V or V dot U, because it calculates the norm of one thing times norm of the other thing times the cosine, and multiplication is commutative. It's a commutative thing, which is not at all obvious, because we know, for example, the cross product is not commutative. It's anti-commutative, right? U cross V is equal to negative of V cross U. Right, so that's true. Another thing is that in each of these arguments, it's linear. So, for example, if I have AU plus BV with a W, where U and V are vectors, and U, V, W, and vectors. So, if this was written in a textbook, it would be this would be all bold-faced font, okay? And A and B will be regular face, so you know that these are scalars and U, V, W are vectors. Okay, so that's going to be same as A times U W, and then plus B times V W. I'm trying to write boldface so that you know the difference. Well, so I'll write commutative. Okay. And this one is linearity in the first argument. Now, because of commutativity, if it's linear in the first argument, then it will also be linear in the second argument as well. Okay. So I'm actually writing two rules at once. One rule is saying that if you have a constant multiple, you can bring it outside. And another rule says that if you have addition, you can split them. Okay. So, and it may look a little foreign, but if you were writing this as a dot product where it looks like a multiplication, it's obvious because it's like if you do this dot with this, what do? You can distribute, right? So of course it's this one and that one. So I'm not writing something that you've never seen before, it's something that you already know. Okay, another important fact is that if you have any vector u and do the dot product with itself, we know that that's going to be norm of u times cosine of the angle between u and u. What's that? What's the angle between the vector and itself? 0. Okay, what's cosine 0? 1. So what do you get?
1.
Well, that part is 1, but
On itself.
norm of itself squared, right? It's norm of u times cosine of the angle between itself, but that's 1, so norm of u times norm of u, so you get that. Or, I mean, just like how we verify that u is equal to a1, a2, a3, if you think of this example and think about what u dot u is, what is that? That's a1 times a1 plus a2 times a2 plus a3 times a3. That's exactly norm of this thing squared, right? So this is obviously true, right? So that's true. But then we are going to state this slightly more generally. So what this is saying is that this implies that u is always greater than 0, except when u is what? U is 0. And then u dot u, or u inner product with itself, will be equal to 0. Okay? So that's true. And this property is called positive definite. So it's called a positive definite property. You might just say definitely positive, but somehow people stuck with this word, positive definite. It just means definitely positive. Okay, so you throw in any vector inner product with itself, of course, it should be something positive, unless it's 0. 0 vector will give you 0, but the norm squared is always positive. Okay, so these are the three important properties of the inner product that we can find out.
Well, what if it's imaginary?
Oh, yeah, so now comes the important part. Thank you for that question. Okay, so, however, here we are assuming So note, we're assuming that the vector space is over the scalar field R. Okay? Usually you put extra bar here. So, yeah. So if the vector space only allows for real numbers, then of course a1 squared plus a2 squared plus a3 squared should always be positive, right? However, if you allow for imaginary numbers, then this would be a little bit murky, right? So, in very rare cases, people just go with this, and then you don't care about this one, and then still do some calculation and call it inner product or something. But usually, when you do a vector, when you work with a vector space over C, for vector space over C, so imagine that what I was calling as like U equals to A1, A2, A3. So think of this vector. Now, being over C suddenly means that these numbers can be complex numbers instead of real. And those actually do help. I mean, you already have seen imaginary numbers being used in real life, right? When did you see it? No? You don't think imaginary numbers?
I'd say maybe in like lab.
Lab? Where? Huh?
Power calculations.
What calculation?
Power,
Yeah. So in analog circuits, when you have RCL circuits, right? When you talk about these, not only you have the amplitudes, but you also have the phase angles, right? So when you represent your current in a way that it represents both the magnitude of the current with the phase, the imaginary numbers do a wonderful job. And it's not a coincidence. It's it really simplifies the math if you allow complex numbers to be in the equation. So definitely there are cases where you want to calculate over C rather than just R. And for that, people still want to retain much of these as much as possible. But then, I guess it's a matter of preference, but then people realize that of these three properties, the most important one is this one. Okay? And for that to work, here's how they defined it. Okay, so if this is called the Hermitian inner product can be defined. Okay, so what's the Hermitian inner product? Well, see, if you have, okay, so first of all, for complex C, there's an important operation called the conjugate that takes a complex number to a complex number. And what it does is, if you have A plus BI, the conjugate, I'm working with engineers here, so I should be using J, right? just so that it's more engineering sounding. Okay, so A plus BJ, and then if you take the conjugate, what happens? The bar of A plus BJ becomes A minus BJ. So the complex conjugate is something that takes J to negative J. Right? where this j is the square root of -1, which mathematicians like to call I, and engineers like to call j. All right, but anyways, let's try this one. Okay. I don't like it. I'll just go back to I. I'm just not used to it. All right, so I'll just go back to I. But anyways, whatever you call it, the important part is that if you have z as a plus bi, then z times z bar has a very interesting expression if you calculate it. So this is a plus bi times a minus bi, right? And that's equal to a squared minus bi squared. Right, all I'm using is the difference of two squares formula, right? A plus b times a minus b is a squared minus b squared. That's what I'm using. But then I squared is what? That's -1, so this is a squared plus b squared. So you have a squared plus b squared as the outcome of z times z bar, but this also has another nice property that on the complex plane, here's the real line and there's the imaginary line. A plus bi is like, here's a and this is bi, and at this point is a plus bi, right? And this length, because this corresponds to the coordinate a comma b, this length is square root of a squared plus b squared. So this really is like the norm of z squared. That's what happens. Does that make sense? Okay. So seeing this and seeing this, people realize, well, I think the correct way to define inner product in the complex world is probably not just multiply two things, but multiply one by the bar of the other. Okay? So that's how they extended the view. And by the way, if you have a real number, taking the bar doesn't do anything because there's no I to change the negative I, right? So even if you work back in the real world, this will be the same formula as before. So I'll show you the formula for the dot product or the inner product between two vectors, and you'll see what I meant by what I just said. Okay. So suppose you have U as A1, A2, A3, and then V as B1, B2, B3. Then U inner product V, where we're not assuming these are real anymore. They could be complex numbers. So if A1, A2, A3, B1, B2, B3 are complex numbers, we define the inner product as A1 times B1 bar, okay, plus A2 times B2 bar, plus A3 times B3 bar. And because of the observation that we had before, the norm of U would be square root of not A1 squared, but A1 times A1 bar, plus A2 times A2 bar, plus A3 times A3 bar, square root, where we just observed that this really, if these are complex numbers, what this calculates is really the length of this complex number, right? Squared, length of this complex number squared. So that's how we're calculating the length of U. And if you take this point of view with this as your inner product, and by the way, this is called a Hermitian inner product. Then this identity still holds. So that's the nice thing. So u would still be equals to norm of u squared, so that u will still be non-negative with equality only true for u equals to 0. Okay? So that part will still be true with this Hermitian inner product. Is that okay? Yeah. All right. But then these would be a little different, right? So let's try to write down what the rules are for the other two properties. So here, properties of Hermitian inner product. Is that if you have uv and if you have vu, they're not really equal to each other. Let's see how it happens. With u and v, the same as before. U is a1, a2, a3, and all that. So uv is what? This is a1 times b1 bar plus a2 times b2 bar plus a3 times b3 bar. But then vu would be what? This will be b1 times a1 bar plus b2 times a2 bar plus b3 times a3 bar. Okay, what's the relationship between them? Is this same as that?
No.
No, it's not true. But then bar of bar is same thing as its original because you're changing the sign of I twice. So what happens is that if you take a1 b1 bars bar, or let's try b1 a1. So if I take b1 a1 this thing and take the bar of it, this is b1 bar and a1 bars bar, and that's same as a1 times b1 bar. So if you take the bar of this, you get that. Okay, complex conjugate of this is this. Yes.
So there's a, because I saw this in like Boolean algebra. Is this Hermitian like?
Oh no, in Boolean algebra the bar is about negation.
Oh,
It's a bit different.
Okay.
But one thing that's similar over there and here is that both the negation in logic and the bar here are what's called an automorphism. It preserves the multiplication. So it's like if you have z1 and z2, you take a bar, the same thing as z1 bar and z2 bar. And then z1 plus z2, if you take the bar, it's same as z1 bar plus z2 bar.
So it preserves
And because it preserves the multiplication and addition, such an operation is called an automorphism. So in that case, so that's where you're finding some similarities there, but that's where the similarity stops. All right, so that's what you're using. So what did we just find? We found out that if I take the bar of this, you get the original one. So therefore, this is equal to this bar. So in other words, if you commute, you get conjugate. So this now becomes, this will be conjugate commutative. And then B, this thing AU plus BVW would be same as AUW plus BVW is still true because if you look at the formula that I just erased, A1B1 bar plus A2B2 bar plus A3B3 bar, the bar is only acting on the second part, right? And it doesn't do anything on the first, so if you have these, you can just see that it's still true. What's not true is that here, because it's commutative, if the linearity was true in the first one, it should still be true on the second one, But unfortunately, what's going to happen is that, so maybe I should write this as a note. Note, let's say you have u times AV, where A is a complex number, okay? Then you can switch this around, put A here, AV here, and then U, and that's going to introduce a bar, right? And then this A is now in the first component, so I can use the previous rule and bring it outside, right? That's going to be A times VU, everything bar. But then that's going to be same as A bar VU bar, which is same as UV. Okay, this overly complicates things, but maybe it's a lot easier if you just look at this. What are we doing really? We're doing A1, A2, A3 dotted with A times B1. A is multiplied to the second vector, so it's A times B1, A times B2, A times B3, right? But then what's the Hermitian inner product? It's this times this conjugate, this times this conjugate, this times this conjugate, right? So all of these eventually become conjugates, so when you pull the A out, what happens to it? A would have conjugate in it. Is that okay? All I'm saying is that this will be A1, AB1 conjugate plus A2, AB2 conjugate plus A3, AB3 conjugate, and then you can bring the A bar out, and once you do that, you see that it's exactly the formula for UV, right? Okay? So it's kind of more obvious if you write it this way, but I just want to use the previous rules to prove it. Okay? But anyways, you see what's going on, right? The second component, because there's a conjugate there, when the coefficient is multiplied, and when that's brought in front, you don't get A out, you get A bar out. Okay? So, because it's only linear in the first component, but in the second one, there's a conjugate linearity happening in the second one. We say this Hermitian inner product is sesquilinear. Okay. So sesqui is like, what's the word? What's the meaning of sesqui? Sesquilinear. It's like it's not semi-linear, or it's not quasi-linear. All those words are actually used in math for something else. And I think all the good words are already used, and people came up with sesquilinear. It's like another way of saying partially linear. Yeah. Sesquilinear. So Hermitian inner product, opposed to the regular inner product, is a sesquilinear product, which is conjugate commutative, and it's still positive definite. So this is still true, part C, and this is positive.
How can you be partially linear?
I'm saying that it's linear in the first component, but then if you had the same thing, if you had U times AV plus BW, these don't come out as A and B, they come out as A bar and B bar. If it was linear, then they have to come out as A and B. So it's not fully linear, that's the point.
Is it like
it's linear in the first component, not linear in the second component. Yeah. But something close to being linear. There's a conjugate operation.
So it's not like a superposition type of thing. It's
No, it has nothing to do with superposition. Okay. It's just something close to being linear. Right? That's what it is. Okay, any questions so far? All right.